Welcome to the 7th lecture in the course on soil mechanics. We'll pass on to the second module, which is on the hydraulics of soils or flow through soils. But I just would like to recapitulate what we did under module 1, which we finished in the first 6 lectures. We looked at the origin of soils, then how they're distributed within the country, the different types of soils. Then we defined terms, which is the kind of language through which we describe the component. The terms like porosity, void ratio, degree of saturation, the water content. Then several other terms called unit weights in terms of force parameters. I would like you to distinguish between total, saturated, dry unit weight or submerged unit weight. If you are looking in terms of mass units, instead of you calling it unit weight, you call it as density. Then, in order to describe the state of the soil or how they exist, we also looked at various other parameters like grain size, which can be determined by sieve analysis for coarse grain material, that is gravel and sand. Then we use the principle of Stokes' law, which gives the velocity of a falling particle for what you call as hydrometer analysis. This is, please remember, is only for the silt fraction. We said 4.75 millimeters to 0.75 or 76 millimeters are sands, 0.076 to 0.002 millimeters are silts, and less than 2 microns is clay, which is a colloid, and above 4.75 up to 750 or whatever size is gravel. So this hydrometer is only for, and then we define some terms here like uniformity coefficient, coefficient of curvature, to show the distribution of the grain sizes at different percentages. Then when you look at the fine grained soil, we need to have what we call as consistency limits. We talked of liquid limit, plastic limit, plasticity index, which is nothing but liquid limit minus plastic limit. Then we also looked at shrinkage limit. This is very good in identifying expansive soil, like black cotton soil. If shrinkage limit is less than 10, you always be careful that the soil can give us serious trouble. So based on this, we also had a plasticity chart where we plotted PI versus liquid limit, and there is an A line which starts at 20% liquid limit. The slope is 0.73. The importance of this A line, which is given by Casagrande, is that silts and organic soils lie below the A line and clays lie above that. We also divided this into 3 zones. If liquid limit is less than 35, we call it as a low plasticity soils. 35 to 50 is called intermediate, and above 50 is called highly plastic soils. So please remember again, soils in this region can be very difficult to handle, very difficult to compact. Then based on all these parameters and distributions, we have given a nomenclature under classification, wherein you can by simple 2 letters signify different types of soils. For example, if I look at gravel, I can have well-graded gravel or a poorly graded gravel, or I can have a gravel with silt, a gravel with clay. Similarly, we can have a well-graded sand, and please remember the first letter gives the kind of constituent, second one is the qualifier, so it depends on the grading. A poorly graded sand, sand with silt, and sand with clay. If the clay percent is less than 10, we don't look at it, clay or silt content. Only when it is more than 10 to 12%, we start including them in the classification. Then when we come to silts and clays, we have ML, MI, and MH. This is a silt of low plasticity, silt of intermediate plasticity, and silt of high plasticity. We have similarly Cl, Ci, and Ch. And if you deal with organic soils, we can also put in these. And based on this, we have several classification charts. The most common one is what is called as unified classification system, which our Indian standard follows. And then we divide the soils into something like A1 to A8, gravel, sand, etc. Then you get highly plastic clays, and they tell you what are the difficulties in handling different type of soils. Then we passed on to engineered fill. Given soil, is there a way in which you can densify that? So what we said was, which means compaction, or shall we say another term we use, densification. How we convert a soil from a loose state to a dense state. How can we do that? We do it by removal of air. And we found out that when you are giving energy by means of a rammer, when you plot water content, oil, moisture content, and gamma dry, very interestingly, you get a parabolic curve, sort of parabolic curve or concave downward, which has a peak value, which we call as gamma d maximum. That is, for a given energy, this is the maximum dry unit weight one can achieve. So you know what is the best that can be possible. That corresponds to what is called as OMC, which is optimum moisture content, and that is somewhere near plastic limit. OMC is approximately equal to plastic limit, but not necessarily true. Could be little less than that, approximately equal to or less than plastic limit. You get an idea. If the amount of water we add is close to OMC and use a certain compactive energy, we get the best density. And the best density also corresponds to highest strength possible. So the soil will have the high strength and also less settlements, least settlement or compressibility, shall we say. The compressibility is the least. So we normally try to achieve this. This is particularly true for construction of embankments, dams, road pavements, etc. We have different machinery for different types of soils. For coarse grained material soils, vibratory rollers are better. Or if you have a very small confined area, instead of a roller, we have a plate, which is usually 300 or 500 millimeters square. It can be even as big as 1 meter square, and it just gives vibrations so that the soil gets densified. For fine-grained soil, we use rollers. It could be a smooth drum. More often, we use pneumatic tied rollers, or what is called in practice is sheep's foot roller, which kind of pushes the soil at different locations. It's called a sort of kneading compaction. That gives the best combination. And then, of course, finally, we looked at how to maintain quality by measuring the density in the field by core cutter method, sand replacement, etc. We also had to make sure that the water content is as prescribed. This is how we studied under Module 1. I would like you to now go to Module 2, which is generally you can say flow through. It's a very interesting topic in the sense that when you look at soil, which is a three-phase material, so you will have voids inside. For example, if I take a section through the soil and these are the grains arranged in a particular pattern, you can see that these spaces are what we call as voids. And if you look at the longitudinal section, suppose I'm looking at a tube or a soil of a given length, L is equal to, let's say, 0.5 meters. And if I add water here, it travels and comes out here. Or, for example, if you have the surface and when it rains, you see that the water goes inside by flow. And how does it do? Because again, these grains are all in a random fashion. So the water molecule may go through this. So the reason why there is flow through soils is because you have voids. Water cannot pass through these solid grains, but it can pass through the voids within the soil. So you need voids. Second thing would be they are all interconnected. If I take steel, it doesn't have any voids. If I take concrete, it has voids of very small size, but they are not necessarily connected, so that water may go inside but doesn't flow out, or very little goes because there are very few interconnected voids. Whereas in case of soil, the voids can be large and they're all interconnected, so that if you allow a water or any fluid, it can go through the soil and come out at the other end. So that phenomenon we can say is flow through soil. And the property that characterizes is defined as permeability. You know the term, a material is supposed to be permeable. When you say permeable, it has a facility for the water or any fluid to go through it. One example in the house would be if you have a sponge. Sponge can absorb a lot of water, and it also allows water to go through that. The reason is sponge has also interconnected voids, and the whole idea of designing or having a sponge is to absorb water, and then of course squeezing it out you can take it out. Similarly here we also use soil, or in the soil the water or any fluid can go through and reach the other side. Why is it important? Because in many civil engineering structures we use soil as a barrier. For example, I want to build a dam so that I can store water. So here is the reservoir on the upstream side. I had to make sure that the losses through the dam are minimum. There is no way you can make it zero because soil still has some voids and there can be some loss. So you would like to know how much. Similarly, you are building this, or think of in terms of a gravity dam on soil or rock, and you are storing water. Now this is suppose is concrete or even masonry. The losses will be very low. I am looking at, for example, Nagarjuna Sagar. It's a masonry dam. The flow through the dam is very, very small, but the chances of the water escaping through the foundation, it could be a soil or it could be rock. Whatever it happens, the reservoir which stores the water may find that if you don't design properly, some leakage. Same thing happens through at the dam foundation, so we need to provide a cutoff, etc. Then second thing would be, I have a retaining wall which I have founded here, and if it rains, what happens? The water may get collected here, and if the water pressure gets stagnated, you will have so much of lateral pressure, the wall may become unstable. So wherever this water occurs in civil engineering, while water is very essential for our living, it gives you problems in terms of stability, leakage, etc. Even in the house you realize that if you don't do a proper job, there may be leakage in the bathroom, in the toilets, etc. So we need to study the phenomenon of flow through soil, which has a lot of applications in real life problems. We also have this problem in nowadays many foundations. People are excavating below ground level. For basements, this is the ground level, and you would like to go maybe something like 6 to 9 meters so that I can get 2 to 3 basements. Suppose the groundwater level is somewhere here. The best way to say what is groundwater level would be, if you go into see a well, you find that here is the well, a open well, the water level may be somewhere here. This corresponds to the groundwater level. The water level below the ground surface, which is a stable one, is what is called groundwater level. This of course may fluctuate. After the rainy season, it will be at the highest, and at the end of summer, dry season, it will be lowest. So it can be fluctuating. Suppose you have to make an excavation. Once you go below the water table, you find that the water will come either from the sides or from the bottom of the excavation. Unless you take care of it, no building and the basement can be constructed. So it has a lot of various applications in civil engineering, and we studied them in order to take care of the ensuing problems. So in order to study flow, you probably would have studied in hydraulics or the course on fluid mechanics. One of the first basic principles is called the Bernoulli Equation, who said that the total head, all h, is equal to the elevation head, the pressure head, plus the velocity head. And I say h is equal to he plus hp and hv. What is he? It's the height with respect to a datum. If I take a datum somewhere, I look at a point here, and this is the elevation with respect to the datum. It can be positive or negative depending upon where you take it. Then what is the pressure head? It's the pressure in the tube. We convert that into head, which is equal to U by gamma W, where unit weight of the soil. You can say that the pressure inside is equal to U is nothing but gamma W into the height of water within that, or HP we say here, pressure head. So that gives me the pressure inside a tube or inside any standpipe, etc. That is what you call as a pressure head. The third one is velocity head is V square by 2G. When you are looking at flow through pipes, canals, etc., conduits, you look at, depending on the velocity, it has a certain potential. That potential is expressed as square of velocity by twice of the acceleration due to gravity, and you will realize that the units of this is nothing but length units. It could be meters, centimeters, etc. In an ordinary civil engineering, when you are looking at pipe flow, conduits in penstocks, etc., where you have a large diameter pipe, the velocity can be high. Or for example, right now many of the rivers are under spate or floods, where the velocity can be high, maybe something like 2 kilometers per hour, 5 kilometers per hour, etc. In that case, this will be significant. But in case of soil, what is the size of the pore? When I am looking at it, you can see that the grain size is less than a millimeter most of the time. So the pore size, you can generally say, is less than 1 millimeter, maybe even less than 0.1 millimeter. In which case, this velocity is very, very small. And if that is so, can I neglect this term? Because this quantity is very, very close to 0 compared to the other two. So please remember, according to Bernoulli, the total head H is equal to the elevation head, the pressure head, and the velocity head. But when we talk of soils, we only talk of the elevation head and the pressure head. And Bernoulli said, after defining this, the flow occurs only because of change in total head. Is flow possible when the total head is the same? Is it possible only if total head is different between 2 points? Suppose I give you a simple example. Let us say we'll take a bucket of water, say bucket, and we fill it with water up to this level. Let's look at the datum here. Take at the bottom of the bucket. This height, let's say, is 15 centimeters. Now, if I want to look at the point A here, its elevation head is 15 centimeters. What is the pressure head here? If I assume the atmospheric pressure as the base, so nothing else is there, so I can say pressure head here is 0. So the total head at A is 15 centimeters. Now let's look at a point which is maybe 5 centimeters from the top. So which means the elevation is 10 centimeters. Let's call this point B. What is the elevation head at point B? It's equal to 10 centimeters. What is the pressure head at point B? Suppose I now put in a tube at the point B. You would agree that the water level will come to the top of the water level here. So can I say this is the pressure head? The pressure here at point B is equal to gamma W into HPB, unit weight of water times the height of water in the tube. So that is the pressure head. So can I now say this is equal to 5 centimeters, because now the water difference in elevation between B and the top of the water level is 5 centimeters. So now the total head at B is also 15 centimeters. Now you find that HA is equal to HB, so no flow. This is just to illustrate it is not the pressure head which matters. For example, the pressure head here is more. If you want to call the port pressure, it is 5 into maybe 9.8. I take 10 as the unit weight. I'll get 50 kPa. The pressure at a depth of 5 centimeters, so this will be 0.5 in terms of kPa. The pressure head at point B is higher. Doesn't mean that there will be flow. There cannot be flow because the total head between the 2 points is the same. So please remember, whenever you talk of flow, always work in terms of total head, which is equal to elevation head plus pressure head. How do we find? I had to take a datum and find out the height with respect to the datum, the elevation with respect to the datum, and this will be the height of water with respect to that point. If I put a piezometer or a standing tube, how high would the water rise in that? So for example, if I put somewhere here inside the groundwater level, this is the groundwater level, I put a piezometer, I can expect the water level to go to the maximum that is possible. So please remember always the two components of the total head, and remember it is only the total head which will cause flow. Just to illustrate now, let us say I take a tube of soil, a cylinder filled with soil. Let me take a 10 centimeter tube. The section is something like this. I filled with soil. I connect this to some water source, and let us say I put in a tube here, and I put a tube here at point B and allow the water to go through. You agree that when I connect it to a reservoir here and the water is allowed to flow, it will flow along the soil and go out here. Let me take the datum somewhere here. Okay. Now the elevation head at point A is HA, or shall we say HEA, whereas the elevation head at point B or for point B is HB. Now if I look at the water level, it's here for point A, this is HA and this is HB. With respect to this point A, the tube water level here rises by a distance HPA. Please remember, if I put a tube, depending on the pressure in the water level will rise in the tube. This is a basic principle you would have studied in all your hydraulics, fluid mechanics. Similarly, when I put the tube at point B, it will raise up to point B here, this elevation HB. So the pressure head here is equal to from point B to the top of the meniscus in the tube. The point I would like to say is that what will be the total head H at A is equal to elevation head plus pressure head at point A. H total head at B is equal to elevation head at point B plus the pressure head at that point. The flow will take place only when there is a difference between these two. We call it delta H, which is equal to HA minus HB. What does it mean? There is a loss in head from point A to point B. The total head has decreased from HA to HB. And what is the difference? Is called delta H. So can I say this is the difference in total heads, or we also use loss in head. You use in fluid mechanics or hydraulics, you say head loss. It's the same, all of them. You know that, for example, if I have a sloping ground and you pour water on the floor, it will flow because the pressure head is 0 on the surface and the elevation head is decreasing with respect to any datum. That is why we say water finds its the lowest elevation and flows always to the lowest point. So basically I want you to realize that unless there is a loss in head, unless the total head decreases, the flow cannot take place. So you can see that the head here is more at point A, the head at point B is less, so the flow will be from point A to point B. This is the basic principle in fluid mechanics, hydraulics, or in soils. So please remember, always look at the total head. And if the total head decreases, changes, the flow will be in the direction in which the head is decreasing. So this being the basic principle, somewhere in 1856, one civil engineer in France came out with a famous law called Darcy's Law. His name is Darcy. He conducted tests in which he has taken a tube of cross-sectional area A and allowed the flow to take place and collected the water here, and he found out that the velocity, let's say the quantity Q is equal to rate into time. The rate is equal to velocity into area, and this velocity, he said, is proportional to the gradient. I is called the hydraulic gradient, which is equal to loss in head by length. I think I forgot to define that term. When we did this simple illustration, point A to point B, you can see that this is the loss in head. Suppose the distance between these 2 points is L. I is defined as delta H by L. What does it signify? It is the loss in head per unit length. That is called the gradient, which is the standard term we use. So you can say either H by L, or if you are measuring in small terms, you can have delta L by H. What he came out with, one of the most famous laws in geotechnical engineering or soil mechanics, is the Darcy's Law. I also would like to mention he is credited with the most significant development in terms of even lifespan. You'll be surprised to know in Europe, the the life expectancy, the normal life, average life people were living was less than 45 years in up to 1856, because they were never having the concept of filtration, good water, etc. So when they were drinking water, they were getting so many problems with respect to their alimentary canal, intestine, stomach, and they were dying. So he designed a filter, and in order to design the filter, he had conducted the experiments, and he found that the velocity is proportional to the gradient. What is the gradient? Loss in head divided by the length. And he found out that this constant of proportionality can be called as K, and K is now called the coefficient of, and this is one of the fundamental parameters that we have in geotechnical engineering. Please remember, what are the units of K? V is the velocity of flow, so it is some centimeters per second, meters per hour, etc. It's a distance per unit time. What are the units of gradient? This is length divided by length, so it's non-dimensional. So you have velocity proportional to gradient, which is non-dimensional, so the units of coefficient of permeability are also centimeters per second, meters per hour, or meters per year, whatever it is you want to say. Length per unit time. Please remember, this is how we can define permeability, and we define the property of the soils in terms of permeability. I just want to mention one last thing in this aspect. When you are measuring the quantity Q, it is velocity into area. So when I am looking at the tube, I am looking at the total area of cross section. So can I say this V is the average velocity? Please note that the water will not flow through this whole area because it has lots of grains, solid particles. But when Darcy looked at it, initially he didn't look at the individual void space but looked at the whole cross section area. So when I am looking at K, it is permeability or coefficient of permeability based on the total area of cross section. So that V is the average velocity looking at the area of cross section. But if I want to now divide this into area of voids, and I say this Q, the quantity rate of flow is V average into A, and I say it is equal to seepage velocity into area of voids alone. I am now looking at only the cross sectional area of the voids. That means if I have total area, you know that area of voids by area total area per unit length. If I do that, this will be volume of voids by total volume, and of course we define it with porosity n. Now you realize that the actual velocity can be higher than the average velocity because Vs is equal to V average into A by area of voids. So V average divided by area of voids by total area. The unit length I can multiply by L and then say V average divided by area of voids into L divided by total area into L, which is equal to V average by N. So the real velocity with which water flows may be higher, and it is called the seepage velocity. Yes, is equal to average velocity by porosity N. So this is the actual velocity which it flows, but we always deal with V because we want to know how much is the void space, etc.